Hello everyone, my name is Quinn and I will be teaching you about calculus, the foundations of calculus, everything you would need for calculus. And this is mainly a playlist that I will be making for IT students in university. Whether you are in high school and you find this playlist helpful, as there are some things that might help you understand, I definitely recommend watching. And to get started, what we will be covering in order will be functions, limits, derivatives, and the application of calculus, also known as optimization, and lastly, integration. Our first topic for this video will be linear graphs and polynomials. Now, linear graphs are essentially the first thing you need to know about linear graphs is that they usually come in the form of y equals mx plus c. Now, x is your input, right? X is your input. Y is your output. M is your gradient, derivative. It has many names. It's commonly known as gradient, derivative, slope, and rate of change. And C is how far it's essentially shift upon the y-axis. Shift upon the y-axis. Right? So the most important thing in our linear graphs is our m, our rate of change. As it suggests, it is the rate at which the graph is increasing and decreasing. You can think of graphs as visual representations of informations, and we're using an equation to represent data. Like, for example, let's say a car is moving at 5 meters per second across a 1,200 meter course, right? We would represent that data with the following. He's moving at 5 meters per second, 5 meters per second. We put our x, our input. X is for seconds in this case. X is our seconds. He's moving 5 meters per second across a 1,200 meter course. So he's moving against 1,200 meters. So this is a visual representation of Sam's running, essentially running. As we can see here, it is borderline just a straight line. So our Sam will consistently move 5 meters every second on a 1,200 meter line. And the equation that represents that environment or situation is 5x minus 1,200. Or let me essentially make the course a tiny bit smaller so we can work with simpler values. We'll say across a 10-meter course. Yes, he's running across a 10-meter course. So at exactly 2 seconds, he will have finished running on that course. It took him 2 seconds to finish this course, as you can see here, where our y is 0, our output. Another visual representation I can show you is what I like to call our spider diagram. Spider diagram is the following, just for some people to understand that the equation here, where Sam was running on a 10-meter course at 5 meters per second, so it will look something like, let me quickly erase. It will look something like 5x minus 10. So we can call this in our spider diagram our processing. This is our processing. Like in IT, as we learned in programming our IP object. So this is our processing, right? Our processing block. Now we need our input and output block. Our input will be here. And as I've stated here, our input in this case is x. In most cases, our input is x. And then we'll put our output block here, right? So let's have our input block here and our output block here. So if we were to put in, for example, we put in 1, right? Let's just put in 1. And the output y. We put our input 1 into this. So 5 times 1 is 5, minus 10 is 5. So our output is 5, right? Our output is 5. And at 2 seconds, we put 2 seconds in, goes through our processing, and our output is 0. So what we can interpret from Sam, who was running on a 10-meter distance course, that he essentially finished running in 2 seconds. Because the minute that it crosses 2 seconds, he is now running off course, because the course is only about 10 meters. If that makes sense? That's essentially more or less about everything you need to know about linear graphs. They aren't too complicated. You only really need to know that x is input, output, and the most important part is the rate of change, also known as gradient, known as slope, known as derivative. It has many names. But this is the most important part to know, and then that c is our shift upon the y-axis. This is how this information helps us to interpret it visually, a graph, or yeah. So let me reinsert the graph real quick. So this is just a visual representation on a Cartesian plane of his performance, essentially, when he would finish. I can restrict by saying less than or equals to 2. Yeah. So this is our Samuel's graph. We restricted it between 0 and 2 seconds since it took him 2 seconds to finish. And that's about everything you need to know for linear graphs. They're quite simple, quite easy to understand. If you don't understand the graph, you can use our little spider diagram here. You put in your input, you have a processing block, and you will get an output. Then